Okay, now that we've studied waveform symmetry and also how to come up with equations for our functions, we're going to begin the Fourier analysis. So at the top of this page, it says, in the early 1800s, Joseph Fourier discovered that any periodic function can be decomposed into an infinite series of simple sine and cosine terms. So this would include any of the waveforms that we've looked at in this class, including those on the page numbered 1 through 12. Our square waveforms, our triangular waveforms, sawtooth waveforms, and so on. So when you do express your functions in this way as an infinite series of sine and cosine terms, you then allow the function to be expressed with a frequency domain instead of a time domain. So again, here's a reminder. These were the 4 waveforms that I presented in the last lecture. We came up with these equations for the waveforms, and yes, we had to use time as our independent variable. So little t was our independent variable. So these were expressed with a time domain. And now when we use Fourier analysis, we will be able to express them with a frequency domain instead. So here is the scary looking main formula for the Fourier series. This one uses summation notation. So there is a term in the front, A0, that's the constant or DC term, and then there are an infinite number of sine and cosine terms. This is what it looks like in expanded form. So if you don't care for this notation, this is what it looks like in its expanded form. So we have an infinite number of cosine terms, an infinite number of sine terms. Out front, we have the constant term. You can see that time is still shown to be the independent variable for the function v at t. And you can see capital T featuring in these formulas. Capital T, of course, is the period of the waveform, okay? Now, what needs to be calculated are the values of A0, A1, A2, A3, and so on, as well as B1, B2, B3, and so on. We use formulas to do those calculations. So here's the formula for A0, AN, BN. Of course, you're noticing they're all integral formulas. In the formula itself, V at t features. And those, of course, are referring to these equations that we worked out in our previous lesson. Okay, we give these terms themselves are given names. So A0, again, that's the term out front here, is called the constant term or the DC component. These first terms here, this one, they're called the fundamental terms. And then we have second harmonics, followed, of course, by third harmonics, and so on. Now here, right here, is why we learned about waveform symmetry a couple of lessons ago. The effects of symmetry are such that some of these operations can be avoided. If a function is even, it will have no sine terms. So what does that mean? That means you would not need to use this equation. if it is odd, there are no constant terms and no cosine terms, which means you would leave out these calculations. If the function has half-wave symmetry, there will be no even harmonics. What does that mean? That means when we are substituting the values of n, here we have our n, n will only be odd, so we will need to work out possibly A1, A3, A5, and or B1, B3, B5. Okay, no even harmonics. So it's important to keep that in mind as well. Okay, now I just want to show you a couple of diagrams. At the very top of the page, this is like waveform 12 on that list of 12 sketches that I gave you at the very beginning of this unit. So this is the full wave rectifier waveform. It's given by y is equal to the absolute value of the cosine of x. So in this sketch, we don't have v versus t, we have y versus x. So the waveform itself is the one that you can see that extends right down perfectly and touches the x-axis. That's the true waveform. That is y is the absolute value of cosine x. The period of the graph is 3. If you consider this to be the starting point of one period and this to be the ending point, that is from negative 1.5 to positive 1.5. If you take this to be the starting point and this to be the ending point, same thing, that's from 0 to 3. So the period is 3 and the amplitude is 1. So you can see the true waveform graphed, but superimposed on that waveform is this approximation. So this is the Fourier series that corresponds to this true waveform equation. This approximation has only 3 terms only. It seems to have a constant term, and also it has 2 cosine terms only. And you can see the approximation superimposed on top. And it's not a bad approximation considering it's only 3 terms. And here's a second example. This, of course, is our square wave. So it's like waveform number 1 in our list of 12 sketches. We looked at this one in greater detail in our last lesson. We had the following formulas for v at t along with these time domains. Okay, so this is the waveform graphed, but again, it's y versus x instead of v versus t. The period is 2 pi. That might be the starting point, that would be the ending point. So this portion would contain 1 full cycle of the waveform. So the period is 2 pi, the amplitude is 1 for this graph. So that is the exact waveform graphed, the time domain graph. And then what do we see here, here, and here? Approximations using Fourier analysis. In this graph, only 2 terms are used. Here, 4 terms are used, and here, 6 terms are used. You can see the approximation getting better and better and better. It would, of course, take an infinite number of terms to produce the exact waveform. But here we have representations using 2, 4, and 6 terms respectively. So not a bad approximation. Okay, within our examples, we are going to need a couple of things to assist us. Because what I'm going to do now is show you how to calculate these things. And I'm going to show you how to do those calculations for waveforms 1, 7, 9, and 5. To assist with that process, we need to be aware of the sine and cosine waves. So this is a document that you will find in the Module 4 folder. Okay, so we've got the sine wave and cosine wave drawn, so we can refer to that. And also here, it's a list of the formulas we're going to be using. So these are the formulas for A0, AN, and BN, which we were just looking at. Where did that get to? Oh, sorry. We were just looking at here, right? A0, AN, BN. So I've put those at the top of this page. And then these are common integrals that come up throughout our examples. So this is the integral of sine and cosine, which the integral of sine is negative cosine. The integral of cosine is positive sine. And what you see in the front here is just the fact that we have to remember to divide by the derivative of the argument. So the derivative of this angle here would be 2 pi n over capital T, the derivative of the angle itself. And so 1 over that derivative is in front. Same thing here, the derivative of the angle would be 2 pi n over capital T. So 1 over that derivative is out front here. So these ones you should understand completely, but I've put them on the formula sheet just for ease. The latter two, you did learn how to integrate these in Math 4. See the difference? We have a t, the variable t in front here, the variable t in front here. These required us to use integration by parts, which you learned just at the end of Math 4. However, when we do our Fourier analysis this week, we are not going to use integration by parts. We are simply going to look up these integrals on this formula sheet. Okay, so make sure that you're ready to go through the lesson. So you might want to have some of these pages in front of you. Okay, so I will stop it here, and when I upload the next video, we will look at waveform 1, this one here, and I'm going to show you how to use the integral to come up with the Fourier series corresponding to waveform 1.